All right, for the rest of the class, let's review what we learned about normal distributions before and apply them also to approximating binomial distributions. So this is our notation for saying X is normal with mean mu and variance sigma squared. There's our mean. This is our variance. Again, as I mentioned last time, some textbooks put the standard deviation there instead. In fact, that's what Mathematica does, is it puts the standard deviation there. But our textbook thinks that the variance is the simpler quantity to work with mathematically. So let's go ahead and put that there. But I will make the remark, or n mu sigma, where that's the mean and that's the standard deviation. It depends on what book you're using. It depends on who your audience is as to which notation is used. What is the PDF? Do I have it memorized? I think so. PDF, little f of x is 1 over square root of 2 pi times sigma times e to the negative x minus mu squared over 2 sigma squared. Double checking, yes, that is a way you could write the answer. It's not, doesn't quite look the same as the book's way of writing it, but it is the same. Okay. To verify this is a PDF, you'd have to verify that the integral from minus infinity to infinity of this thing equals 1. Is that easy to do? No, it's not. That's not an easy thing to do. Could you have Mathematica do it? Yeah, you can have Mathematica do it. If you had to prove it by hand, it's hard. In fact, the best way to approach it is with a trick involving multivariable calculus and polar coordinates of all things. And maybe because of that little hint that I just said, maybe that wouldn't make it surprising that pi somehow becomes involved in it. Why is pi in there? Okay, it's because of that. Symbolically speaking, it's because of that translation to polar coordinates, and because of polar coordinates, circles become involved. Not going into details because it's multivariable calculus, advanced multivariable calculus at that. That's the PDF. What's the CDF? Capital F of x. Well, it would be the integral of the PDF from negative infinity to x. And I think I will go ahead and use a xi here for fun. F of xi to xi. I love saying that too, xi. That is the CDF. What's its formula? Well, it's its own formula. You can't really write it in terms of functions you're used to. Really? Mathematica. Really? What is CDF normal distribution? Mean mu standard deviation sigma. Mathematica does the standard deviation there. IRFC. What's that? That's called the complementary error function. What's that? The error function is defined as an integral. And it can be proved you cannot write it in terms of finite combinations of polynomials, rational functions, square roots, cube roots, blah, 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 trig functions, logarithms, exponentials, everything you're used to from calculus. You can't write it in terms of finite combinations of those things. Can you write it as infinite combinations? Yeah, you can have infinite series representations of it. But we'd prefer not. So it's just a new function. It's a new function. There's plenty of functions you've never heard of. But before this class, you never heard of the gamma function before, right? Maybe, most likely. But now you've heard of it. There's hundreds, if not thousands, of functions you've never heard of before. In fact, you could even create your own functions and name them after yourself. And you can even patent it. Nobody will care, but you can do that, I think. You got to pay money when you patent it, though. So, you better be confident that you can make money off of your new function. You can approximate values because defined as an integral, you can approximate the integrals. You can get numerical approximations. You can use left-hand sums, right-hand sums, trapezoid rule, midpoint rule, Simpson's rule from Calc 2. Simpson's rule is probably the best to numerically approximate, although it is an improper integral, which makes it a little tricky. Though the area, once you're far enough to the left, is so tiny, it's negligible. Can effectively be ignored under a normal curve. When you're far enough to the left, how far is far enough to the left? Well, the 90, 68, 95, 99.7 rule says 99.7% of the area is within 3 standard deviations of the mean. This area is 99.7%. 99.7% as a probability, it's 0.997, very close to 1. Only 0.003 to either side. Yeah, once you're past 3 or 4 or 5 standard deviations, if you want to play it safe from the mean, the area is really negligible. In approximations, you can effectively ignore it. In the case where the mean is 0 and the standard deviation and also variance is 1, we do typically use the letter Z for a standard normal random variable. Standard normal random variable, mean of 0, both the variance and the standard deviation are 1 because, of course, 1 squared is 1. Square root of 1 is 1. It's also true, I forgot to mention, that the inflection points of the graph, and my graph is not to scale, are both exactly 1 standard deviation away from the mean in the x direction. And that means with the standard normal centered at 0, standard deviation of 1 means 1 is going to be about right there, and negative 1 is going to be right about here under a standard normal for a standard normal distribution. Historically, standard normal distributions were super important so that people could calculate probabilities. Maybe a little less so today because we don't need to convert to Z to use some table to convert a probability. We got our calculators, Mathematica, spreadsheets, all that sort of stuff that can compute probabilities for us. But I think it's still important for people in this class and also in intro stats classes to get a little practice with writing probabilities in these kinds of situations, both symbolically and maybe even using the table a little bit. It's worth practicing. So say X is normal with a mean of 3 and a variance of 16. So the standard deviation would be 4. Okay, I could have made that not a nice number. You should be able to deal with situations where the standard deviation is not a is an irrational number like square root of 7 or something. If I want to find, for example, the probability that X is between, say 2 and 5, I do want you to be able to, on exam 2, show your work symbolically here by converting to Z, writing the answer perhaps as a difference of CDF values before you use your technology. It's an important enough skill that I want you to be able to do that, even if you don't always do it on homework. Convert to Z, so we need to subtract the mean and divide by the standard deviation, not the variance. I talked about this last time. I'm using the transformation. Z is X minus mu over sigma. Divide by the standard deviation, not the variance. When you do it with X itself, it becomes a Z, not because of magic, but because of how we've defined it. And this becomes what? The probability that Z is between negative 0.25 and positive 0.5. And that'll be capital F of 0.5 minus capital F of negative 0.25. Once again, it doesn't matter whether you use less than or equal to signs or less than signs in these things because it's the same probabilities. And then you can use the technology, or let's get a little practice with the table. Table we're after is the standard normal table, cumulative distribution, standard normal. It's page 697. It's values of capital F sub Z. So capital F of 0.5, look at the next page, look for Z as 0.50, corresponds to that area. 0.6915 is the area to the left of 0.5, 0.6915. 0.6915, and then the area to the left of negative 0.25 is on the previous page. Negative Z values, look for negative 0.2, and then 0.5, that's the 0 column, 1, 2, 3, 4, 5. It's the area to the left of negative 0.25 is going to be 0.4013. Approximately. So the answer is approximately do this in my head, 0.22902. How about that? I did that in my head. Is it right? Well, it's an approximation. It's possible, especially if the numbers that are here and here are not so nice, or you're approximating those, that you get something different than your calculator gives you. But these are nice numbers, so I think this is going to be what our calculator gives us. And you could do it in two ways. You could either use a standard normal, which is what the calculator is set to by default, and make your lower negative 0.25 and your upper 0.5. 0.2902. Yep. Or we could do it with the original X variable, where the mean is 3 and the standard deviation is 4. X is going between 2 and 5. 3, 4, standard deviation. They're not variance. Same answer. Okay. And again, because the numbers worked out so nicely when you converted to Z, these turn out to be the same. Again, if you round the Z's to 2 decimal places and use the table, it doesn't necessarily give you the exact same thing the calculator would. Calculator is technically more accurate because you got more decimal places. But to tell you the truth, in reality, if you're thinking about significant figures, we should probably be rounding this to 0.29 anyway, instead of 0.2902. It's pretty rare that you would say I'm modeling this situation so accurately that I can estimate probabilities to 4 decimal places. That would be a pretty rare thing. Maybe 3, 4 is getting a bit questionable. If you're thinking in terms of significant figures. By the way, I think I mentioned this the other day, but the standard normal random variable has a standard symbol for its CDF, and it's not capital F, it's capital B. That is a standard symbol for the CDF of a standard normal random variable. It's called capital Phi. You'll see it in some books. Our book doesn't bother with it, but you'll see it in some other books and maybe online and that kind of thing. Okay, so if you do, that's just standard notation for CDF of a standard normal random variable. All right, in our last 13 minutes or so, let's talk about binomial, normal approximations to binomial. Which again, as I hinted at last time, is a little strange because, well, binomial random variables are discrete. Say X has a binomial distribution with parameters N and P. So what is the situation? You're counting the number of successes, like number of free throws made in N trials where P, your probability of success, stays constant, and also the trials are independent. The PMF, probability mass function, involved n choose x. Remember that? N choose x times P to the x times 1 minus P to the n minus x. A table in the book for the CDF values, which are sums of those things. Mostly you probably used your calculator. It also is true that the mean was n times P, and that makes good sense. If I'm a 40% free throw shooter, not so good. And I attempt 20 free throws. N is 20, P is 0.4. I would expect to make 20 times 0.4, 8 of them or so. Does that mean my probability of making 8 is pretty high, like bigger than 0.5? No. Though it probably is the highest probability. The variance turns out to equal, it's a little less intuitive, n times P times 1 minus P, or n times P times Q if you define P to be, or Q to be 1 minus P. And that also means the standard deviation is square root of that. Again, where Q is defined to be 1 minus P. P is the probability of success. Q would be the probability of failure. Can you simulate binomial distributions on Mathematica with random variate? Yes, you can. Random variate binomial distribution. Oh, say 20 free throws with probability success 0.4. This time I made 7 of them. The next time I made 7. The next time 12. Got really lucky there. The next time 8. Do this 100 times. I've got 100 simulated experiments of attempting 20 free throws and keeping track of how many I make. Call this data. I don't have to call it data, but can I make a histogram of that? Well, yeah, but it's a histogram for a discrete random variable. These are counts of actual numbers. The number of 4s, the number of 5s, the number of 6s, 7s, 8s, 9s, 10s, 11s, 12s, 13s. Whereas with the continuous case, we were counting the numbers of values in intervals. So it's a little different interpretation of the histogram. You could say it kind of looks like a normal curve. Okay, let's do more of them, like 10,000. Oh, that's a lot of free throws. That's going for the rest of my life. Okay, that's looking more like a normal curve, isn't it? What normal curve can I use to model this shape that I see? How about a normal random variable, y? Oh, with mean equal to n times p and variance equal to n times p times 1 minus p. How about that? Makes logical sense, right? That's probably the best thing to try. I'm not saying it's going to end up with good results, but that might be the best thing to try. So once again, let's go back to the free throws. Let's say n is 20. P is 0.4. I might wonder, when I attempt 20 free throws, what is my probability that I make between 8 and 10 of them inclusive? What is that probability? According to a binomial distribution involving n choose x, I could figure out the exact answer according to the binomial distribution. Now let's do it with PDF. For example, my probability of making exactly 8 free throws is about 0.18. Making 8 or 9 is about 0.34. Of making 8, 9, or 10 is about 0.45. The answer here, according to the technology, is about 0.46. What if I didn't have Mathematica? And I was unsure if a spreadsheet could do it. Actually, a spreadsheet can do it. Maybe I don't have a spreadsheet either. But I do have a handy dandy normal curve table, standard normal curve table. And I noticed I know the binomial distribution, even though it's discrete. If you make a histogram of the probability values, PMF values, it looks like a normal curve. Could I approximate this using area under some normal curve? Yeah. But it's a little tricky. You have to use something called the half unit correction. In this case, the y is going to be normal with mean 20 times 0.4 is 8. Variance 20 times 0.4 times 0.6 would be what? 4.8? That's 20 times 0.4. There's 20 times 0.4 times 0.6, right? 4.8, does that sound right? Doing calculations in my head is dangerous. That's one. Yeah, okay, that's right. 20 times 0.4, 4.8. That's the variance, not the standard deviation. If I'm thinking in terms of areas under a normal curve that would fit here, I'd be really trying to approximate the areas of these three bars. The vertical scale would be incorrect, right? Because these numbers are counting how many data values are in each. How many times do I make it? 8 times, 9 times, 10 times. It's not a probability density. These numbers would need to be less than 1 if they were going to be a probability density. But if I imagine these corresponded to probability densities, I would be trying to find the areas of these three bars. Those don't go from 8 to 10 under a normal curve. They go from 7.5 to 10.5. 7.5 right there to 10.5. If I'm imagining a normal curve following this pattern here. And if I'm imagining the vertical scale as probability densities and the areas being what I'm after to find probabilities. So yeah, I need to approximate the probability that X is between 8 and 10 by saying it's approximately the probability that Y is between 7.5 and 10.5. And if you're unsure, should this be a 7.5 or an 8.5? Should this be a 10.5 or a 9.5? The picture is the key. Draw a little picture, even if it's not super accurate, of like a little histogram showing you what bars you need to approximate the area of, and label the whole number values in the middles of the bars, like 8, 9, and 10 are in the middles of these bars, to figure out the area that you're after. And if all I have is a standard normal table, I also need to convert this to z-scores. Subtract the mean of 8, divide by the standard deviation, square root of 4.8. Careful, a common mistake is to divide by the variance, but no, you got to divide by the standard deviation. And this is still continuing approximations. So negative 0.5 divided by square root of 4.8 is about negative 0.23 if we're rounding to the spots we can use for the table. And 2.5 divided by square root of 8, or 4.8, is about 1.14. I'm going to the table. I look for 1.14. I'm not going to show it to you here. It gives me about 0.8729. And then I look for the negative 0.23 on the previous page, and it gives me 0.4090. Do the subtraction, 0.8729 minus 0.4090. I get 0.4639. About 0.46. How about that? Same answer to 2 decimal places as I got up here. Is it going to be the exact answer to 3 or 4 or more decimal places? No. But in this case, to 2 decimal places, it was the same. By the way, hang on here. I can use the normal approximation to calculate even an individual probability, like the probability that x equals 8. Exactly. Use the half unit correction in both directions around 8 to do it. I'm not going to go through the details, but that's what you would do. It can be done. Historically, I'm not a complete expert on the origin of the normal distribution. I know Gauss possibly was the person who created the normal distribution back around 200 years ago. Maybe others did, I'm not sure. Sometimes it's called a Gaussian distribution. I think one big motivation for Gauss was computing binomial probabilities, if I remember correctly, for large values of n. Because computing n choose x when n is very large, involving factorials, is before technology. So the normal approximation to the binomial was certainly very important to Gauss and his contemporaries 200 years ago. It was important before we had high technology with calculators and computers, even 50 years ago. But even today, it's still worth learning. Okay? If nothing else for historical reasons, but I think it's still just good to know. And by the way, you can use normal curves to approximate other random variables as well, including Poissons. Okay? So it's a pretty universal thing. It's a very important distribution. Have a good day.